It's July 31st. Well, first thing is I'm not dealing with this problem anymore. There's gotta be a moment that you realize, nah, I don't want to handle this anymore. So I ignore the magic solution from Lee 215 and then close it. That's it. That's it from me. I mean, we will probably revisit once if we ever encounter this problem again. But right now, at this moment, I am happy with the solution I have, which makes sense to me. So that's that. That's it. I don't want to deal with this anymore. Secondly, we're writing some tests today for the React Native app today. Boy, it took me like 5 hours, maybe 6 hours. Still couldn't figure out a better way to do this. What happens is, it seems like the fake timer, I think like about a month ago, I'm doing exactly the same thing. And then I thought I figured out how fake timer works. But actually I don't. The fake timer, it seems like if you have some like use effect outside the set timeout, right? And then that use effect does some async calls. And then you use fake timer. Then the fake timer, as it progresses, it does not take into account any of the async calls outside fake timer. So that means if the code inside your set timeout is dependent on state changes that happens outside of set timeout and also under async, then the effect will not be reflected inside the set timeout. Basically, just means whatever happens inside a timeout, set timeout is the only thing that can be recognized during fake timer progress. So it took me a long time to kind of realize that, and the test has to change, right? I mean, I have to do something to ensure that the test can work, even if we don't do any of the async calls outside set timeout. And I'm using a little hack right now, and I kind of just realized you only have so much effort, so much time, and so much ghana to go down one rabbit hole and try to solve it. And after a while, you still cannot solve it, and you're like, screw this. We're not wasting more time on this. We're just going to use some other methods. And usually there are, other methods that are able to solve the problems. Just a little bit hacky, a little bit less elegant. But hey, that doesn't matter. As long as I solve the problem, we'll deal with the hackiness in the future. Anyway, so that's today. A lot of coding. I need to kind of get back into this rhythm. I need to do I need to do this thing, this app, like after I get back from work. But I need to kick a start, right? Like if you have the momentum, and then it'll be easier for you to keep going on. You see, like today it took like 5-6 hours to get the momentum. That's I can't just say, get back from the work, like 9 o'clock, sit down and try to get a momentum up. It's impossible, because you look at the code and you just after 10-20 minutes you're gonna give up. It's just not working. But today it's different. You have the entire afternoon. You can just grind until you start to feel, okay, now I think I have the momentum. Yeah, now I have the momentum. So I have the momentum both for my work and for my personal stuff, which is great. That's exactly the state I want to be in. Alright, so that's that. Now let's go to unique path. This is today's thing. I remember this one. There's a robot, okay. Top left corner tries to move to bottom right corner. The robot can only make move down or right. Given the two integers m and n, return the number of possible unique paths that the robot can take to reach the bottom right corner. So you can only go down or right at any one point of time. Isn't this? I feel like there is a way to calculate this, right? We don't even have to do. You can't, right? You can't. See, otherwise you have to go ON. That would be huge, right? That would be huge. Oh, 100, 100. Yes, you can. You can just iterate through every single one. But remember, there's a way, because you can only go down or go right. So we can go. I can go all the way right and down, and every. Screw this. Let's just think about this as. Oh shoot! This is. We need to. Wow. August. Time flies, man. Time flies. Very soon, you'll have to go back for your PhD stuff, which doesn't seem to be very promising at the moment, but we'll figure it out. And then, once you figure that out, very soon it's gonna be, Christmas, and then New Year, and then summer, and then you're supposed to graduate, and then you start working, and then life just moves on so fast. Okay, so we are going to use the most stupid method. Yeah, and I'm pretty sure they gotta be a smart method. Hold on, we can do this, right? So I'm trying to do it without using recursion. Well, recursion will be the easiest way, right? But let's say bottom up. All right, let's say how many different ways to reach here. So it will be the number of different ways to reach from here, and a number of different ways to reach from here, right? And that will be the sum of these two. And how about this one? How about this one? It'll be sum of these two. So this one was sum of these two. And this, so isn't like going this way. So the number of different ways to reach here is 1. This is a 1, right? And then this is also 1. So 1, 1, 1, 1, 1, 1. And then second row, this will be 1, and this will be 2, right? Because I have 2, and this will be 3. Let's draw it out. Come on. 1, 2, 3, 4, 5, 6. So this is 0, right? And we want to find any, because I can only go 2 ways, either go down or go right. So the number of to go this, add a number of to go this, yeah. So it would be 1, 1, 1, 1, 1, 1. And then this will be 1, right? This will be 1. 2, 3, 4, 5, 6, 7. And then this will be 3, 6, 10, 15, 21, 28. Yeah, that is the solution. Is there a way to make this computation a bit easier? So it's 3 plus 3 equals this. 3 plus 3 plus 4 plus 5 plus 6 plus 7, right? So this is just like all of these 1, 2, 3, 4, 5, 6, 7. And then this is going to be 1 plus the sum of this. Alright, it's 5, 10, 14, 20, 28. So if we have another one, it'll be the sum of this. How can we calculate this one faster? There's gotta be a formula. I don't know. Is there a formula for this? Screw this. I don't know if there's a formula, but here's what we're gonna do. We're gonna say dp equals 1 times n. I think m is, 1 times n. And I say for this in range m, for I in range, let's say 1 to n, dpi equals dpi plus dpi minus 1, which can be translated to plus equal. And then we are going to return dp minus 1. Let's see. 37 is 28. 32 is 3. Anything more? That's it. Oh, what the hell? It's not right. Come on. dpi plus dpi minus 1. Oh, I think maybe n minus 1. There we go. Hey, can we like simplify this? I don't know. Whatever. This one should be right. So let's check edge case. 1, 100, 100, and 100. That's kind of good edge cases. I guess it's too big. Oh, what the hell happened? Oh, it has to be, okay. Hold on. Are you telling me 3, maybe 4 will be very big? Oh, yeah, it can get very big. I feel like there should be a math solution. Let's see if I have a math solution before. 62. 1d dp. And then there we go, math. Ooh, yeah. The Pascal triangle. Dang. Yep. You're right. It is the Pascal triangle. Oh, yeah. What's the Pascal triangle? That's the math. Yeah, I knew it. I knew it's going to be bottom up with Q. What? That's supposed to be top down. Oh, the Pascal triangle. Then which one? Yeah, it is factorial, right? So, oh, I forgot the. Which one should we? I don't even know which one to click on. Or it's just n choose m. Yes, it's just n choose m. It's just n choose m. Like, oh yeah. Now I remember. Yeah, this is just n choose m. So if we extend, that will just be 3 choose 1. No, 2 choose 1. No, 2 chooses 0. 0, 1, 2. Right? So 0, 1, 2. Choose 3, 4, 5, 6. 7. Wait, hold on. 1, 2, 3, 4, 5, 6, 7. That's actually choose 8. Right? So 8 choose what? 8 choose 8 choose. See, this is 0. 1, 2, 3, 4, 5, 6. 8 choose 6. Yes, 8 choose 6. So if we do a Pascal triangle, so this is a Pascal triangle solution. Import mass. So we're gonna say choose 6. How do we reach 6? Well, that is just gonna be, if we have one more, we end up here, then we'll say this, and then we'll add 1, right? So it's gonna be this. How much we have here, and then here. So it's m plus n, right? We say 1, 2, 3, 4, 5, 6, 7 plus n minus, I'll say minus 2. So that will be 3 plus 7 is 10 minus 2 is 8. And if we do 4, that'll be 9. So it will be this choose. So I think it will be m plus n minus 2 choose what? Well, if we want to choose, I'll have 1, an additional 1 here. So it has a 1. Alright, that's a 0. 1. 0, 1, 2, 3, 4, 5. It's always 6. Right? Is it 6? Because we're basically hauling on this way. Let's see, 28, right? We have this line is 28. Should be this one, 84. 0, 1, 2, 3, 4, 5, 6. It's always 6. That's isn't that just choose n minus 1? That's what I think. Okay, how to do this? N choose m. And it's n factorial divided by m factorial and n minus m factorial, if I'm not mistaken. So I can say math dot factorial n is m plus n minus 2 divided by m is n minus 1 times math dot factorial m plus n minus 2 minus n plus 1. So this and then this cancel, and this will cancel. So that's my solution. Let's see. Okay, looks good. Is this correct? Yeah, I think it is correct. Oh, wow. Okay. Not complaining. All right, so we got this one done. All right, take a look at this one. It's 11:14. I don't think I'll be able to do it. Oh, God, 4. Concert, n rows numbered 0 to m minus 1, okay? Each with m seats numbered from 0 to m minus 1. Need to design a ticketing system that can allocate seats in the following cases. If a group of k spectators can sit together in a row, if every member of a group of k spectators can get a seat, they may or may not sit together. Wait, hold on. If a group of k can sit together in a row, if every member can get a seat, they may or may not sit together. Spectators are very picky, hence they will book seats only if each member of the group can get a seat, with row number less than or equal to max row. The max row can vary from group to group. In case there are multiple rows to choose from, the row with the smallest number is chosen. There are multiple seats to choose to see what the small number is chosen. I don't understand. What does this mean? This is just an if. Can sit together. Then what? Do they sit in together in a row? If every member of a group of k spectators can get a seat. design a system that can allocate seats. So it will allocate seat in the following cases. Allocate seat if, okay, I think you should read this way. Can allocate seats if a group can sit together in a row. Then we'll allocate seat. If every member of group can get a seat and allocate seat. Okay. So if everyone can sit in a row, I will allocate seat. But if they cannot sit in a row, but every member of a group of K can get a seat, I'll allocate seat. They may or may not sit together. Okay, I think I know what it means. They will book seats only if each member of their group can get a seat with a row number less than or equal to max row. Max row can vary, so we have a max row, so everyone want to book seats with row number less than or equal to, okay? In case there are multiple rows to choose from, the row with the smallest is chosen, okay? Multiple seats, the seat with the smallest number is chosen, okay? So book my show, N and M. Initialize objects, N as the number of rows, M as the number of seats per row. Oh, I hate this. I'm going to swap these two. How can you have N as the number of rows and M as the number of seats? I will swap these two. Gather returns an array of length 2 denoting the row and seat number of the first seat being allocated to the K members of the group who must sit together. Oh, gather, I see. In other words, it returns the smallest possible R and C such that all C and C plus K minus 1 seats are valid and empty in row R, and R is smaller or equal to max row. Makes sense. Return is not possible, okay? Return true if all K members of the group can be scattered, allocated seats in row 0 to max row, who may or may not sit together. If the seats can be allocated, it allocates K seats to the group with the smallest row numbers and the smallest possible C numbers in each row, otherwise return false. Okay, let's see the examples. So 2 rows, yeah, I'm gonna change this. I ain't gonna call this, I don't call this, this is how I know. So 2 rows, 5, so we have this, 2 rows, 1, 2, 3, 4, 5 seats per row. I would say gather 4, 0. Okay, 4, 0, that means I want max row is 0, and I want 4 seats, and then we go 1, 2, 3, 4. So the first one is 0, 0, right? Okay, then I gather 2, which I can't because 0 I only have 1 left. Then I get 1, and I get 5. True, because I can just do 5. And then I want to do 1, 5, 5, 1 again. Cannot do because we don't have any seats left. Interesting. Yes. N, M, oh, N is number of rows. Yeah, still, so M is the number of rows. N is number of seats, max row. Okay, so you need to basically record, right? Is it deterministic? What if the first call is scatter? That's a good question. Why don't we try it? So what if I scatter first? And I scatter, let's say, this. So I can pick 0. Oh, if I multiple, then it has to go. Okay. So, all right. So when it's empty, a scatter for 1 is equivalent to gather for 0. It's the same thing. It's exactly the same thing. We can actually just do this one more time. I think it will return exactly the same answer here. Output. True. Yes, gather is true. This and true false. Yes. Okay. It is deterministic. Every time you call, it's deterministic. So the problem is not to find an optimal way to branch out, but to find an efficient way to represent the state of the seeds. The state of the seeds. And we have how many rows? We have 5 times 10 to the 4th. That many rows. So basically, you're given a max row, right? So from 0 to max row, you need to know quickly to query, right? From each row. This feels like data engineering, right? So you might have to cache some stuff. Like, how do you cache? What type of data structure? Well, I kind of feel like segment tree because it's kind of range, right? You have a range. I'm not quite sure. I guess let's just see this example, 4, 0, right? You want to gather 4, 0. And right now it's empty. How do you know it's empty? And I can record because everybody want to go lowest, want to go the leftmost, right? So whether you gather or whether you scatter, it will all be consecutive. It will always be consecutive because that's what they prefer. So if that's the case, then what we can do is for each row, we only need to record the last or the first empty seeds, right? So now we have one array of size n. Maybe that's why they want to keep size n. All right, I will entertain your idea of doing n rows and m columns. Okay, so now we have an array of size n, and each one represents the first empty seed. So at the beginning, it will be 0. Everything will be 0, right? So then, when you call, right? When you call, you say, okay, I want the maximum row, okay? So from 0 to the maximum index we have within, right? If it's gather, then we need to find an index when m minus this index plus 1. Actually, it's m minus 1 plus this index. Minus this plus 1. So just m minus this index, exactly. M minus this index is larger or equal to k, right? We need to find. Then the question is, how can we do this fast? So again, what do we want to find? We want to find if there exists a value such that m minus k is larger or equal. Now m minus this index is larger or equal to k. Or we can say m minus k must be larger or equal to this index, right? So if we use m minus k as the target, and if we can sort all the things, right, then what? Then we say we can binary search, right? We can binary search then because it has to be smaller or equal to that value, right? The index has to be smaller or equal to. So now we have a bunch of indices that can satisfy. And then within those bunch, we want to find the smallest index. Yes, the smallest index among the ones that satisfy. And after that, we increment the value of the array. Okay, so we have the value of the array, and then we can take this. Then how do I find exactly? How do I find? I cannot sort every single time. So it's like giving me a range. I have the maximum value I can have. The maximum value is m minus k, right? That's the maximum. It can be equal to that. We have the maximum value. So what we want to do is, given an array of integers, tell me what is the maximum value. No. Tell me the minimum value. If the minimum is larger than the max, then that's an impossible. Okay? If minimum is smaller, then I want to know in which section then we have the minimum. So we can split in half. Binary. It's not binary search, but it's segment tree. So we find the smallest in this range, and it's small. Then we go the left branch, and we go the right branch. So the left branch will find the smallest. If it is smaller than the max value, we keep divide, go to the left. If it's still smaller, until we find a left that is bigger, then we go to the right. And then we find some. So eventually, it is a binary search to locate the smallest, not to locate a But yeah, if we find the smallest value, right? If in the range the smallest value is larger than this, then it means it's not possible. So we just try to locate the smallest value that is also the leftmost, right? Almost the most to the left. And once we find it, we will update its value. And this is a segment tree. So we can use segment tree for gather. Okay. I see how segment tree can be used. So the gather would take log n. So log n squared, it feels like. Because each one is, and then so it's like a log. Yeah, log n squared. Log n times log n time, I think, for gather. How about scatter? Now scatter is a little bit tricky. Because scatter requires, what does scatter require? Basically what scatter says is we just want to fill. Scatter. Can we just iterate through? Or can we maintain a prefix sum of the number of seats available for each row? Then you have the update. 2 bit? Come on, you're kidding me. So the first bit, we will store the smallest value. No, not smallest value. We'll store the index, right, for each one. And oh yeah, it is. We want the smallest index, right? We want the smallest index. And then, because that's what we want to query. That's what we want to query, the smallest index. Actually, how would you query the smallest index? How do you update? So again, this value, we can have original value and we can have a new value. Okay, so that's like a delta. But a delta, the delta should just be the value itself, because was not adding every time we update. We will just compare the previous smallest with the current value. Hold on. Smallest value when you update. Oh man. So this value is this getting bigger. If it's bigger than before, what do we do? I've seen it done before. You can do max and the minimum. I just forgot how it's done. Yeah, which is the min, which is, I think it should be fine. And because each time increase. Ooh. What if we change it the smallest? Then what do we do? Hey, how do we do that? Segment tree to maintain the smallest value in the segment. I got confused. Because if we do a sum, we just add a delta to it. And everyone will be affected by this delta, right? But if it's finding the minimum value, now we change this, let's say, by adding some value to it. Okay? By adding some value to it. And then, how do I know if this is the original? Right? You don't know. Shoot. Yeah, that if we can not solve that, it is not possible to solve this problem. But I've read before, it is possible. It is possible to find, to maintain the minimum, the maximum in segment tree. Just don't remember how to do the update. Range minimum, yeah. This is what I want to find. I don't remember how to do this. Yeah. How? No, we don't want to do that. What the hell? Jesus. Yeah, that's true. When we query, it's easy. Right? Minimum value of left and right. Yeah, query shouldn't be too difficult. Query. But if you want to use BIT, how do you query? So the query is from 0 to this index. So let's say minimum of this and a minimum of this. And how do you know a minimum inside that? Alright? How'd you do minimum inside here? It's a good question. All right. So we can, like, we don't know. Oh man, now we have to write. Hold on. Let's ask a binary indexed tree. Okay. Min query. Can we do this? I'm not sure. Is it possible? For any invertible operations. This one says it's possible. Oh, people asked this already. 7 years ago. Update value at a given index. Query. You gotta be giving 2 Fenwick tree. Maybe we have to just go back to the binary tree, huh? But in general, it is not. So we have to use segment tree. Yeah, let's just use segment tree then. Which is, honestly, it's not too big a deal. We can write segment tree on that. Yeah, let's just go with segment tree. Okay, so we know segment tree is possible. So yeah, again, the first problem is solved. But the scatter. So the scatter, if I know the range, that's actually a range sum, right? We have this, 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 everything we have, the number of remaining seats, okay? Number of remaining seats. Number of remaining seats. Then we can build a segment tree to query the maximum. Okay. Number of remaining seats. So one segment tree to query the maximum, and one binary index tree to query the sum. Okay. And then for scatter, what do we need? For scatter is we just need to find the range. But how do we know? How do we know which range to use? So let's say the scatter give you k, a certain value of k. We just binary search. We're going half, right? We calculate what's the number, okay? No, not half. We from the max row, right? So we have max row, then we know the total number of seats from 0 to max row. That's BIT, that's binary index tree, right? So we know that. And if it's smaller than what's needed, then it's not possible, okay? If it's larger, then we slice this in half. We find the first half. If the first half is smaller, then what? The first half is smaller, but whatever value the first half is, if it's smaller, then we're going to minus that, and in the second half, our target becomes small, right? And, once we've done that, then these are just discarded. So we need to have like two indices, right? We have two indices. Oh, shoot. How are you going to update? Well, you don't have to update, right? I mean, gather, when you update one, so that's O log n. When you scatter, we'll always do the first few. And if the first few are done, let's say at a certain point, those will all be filled, right? If it's just one, then we just update that one, which is fine. If we have multiple, then those are gone. How do you handle the situation of gone? Oh, which is fine because I just don't care about it, right? I just minus that. So we don't have to update. Let's say we have to throw away the first 100 rows, right? Because they will all be filled. And then we just need to update one row. And that row will be the starting row, okay? And we'll add to that row, and everything after that will be updated. And then next time we query, it's going to be from that row to the max row. I think we have a solution. We need a segment tree to handle max row, the max query, and we need we use binary index tree for the scatter. So gather and scatter will use 2 different trees. And holy guacamole, for the 2 different trees we have to update both. Man. Update both. Yeah, it's fine because I specify which range to do. Okay, so we're gonna try tomorrow. Wow, that'll be fun. That'll be very fun. Okay, I'll see you guys tomorrow.